record. Okay, so the final lecture of the machine learning and pattern recognition course is on decision trees. And this lecture I start in a completely non-standard fashion because I give the pros and cons. And why is that? Because understanding how decision trees work is, I would say, completely intuitive and clear. Yeah? So if we have a decision tree, we are given some possible set of observation or measurements, which we'll call X. Now, there are more complicated options, but usually you start with some X. I will denote it 1. I'll put it maybe in brackets here. And we ask whether it's above or below a threshold if it's numeric. And in that case, if that condition is satisfied, we go left, else we go right. And then this repeats until we end up somewhere in a leaf. And in the leaf, we make a decision. So the decision is a function of the leaf. Now, of course, things can be, as you can imagine very easily, can be slightly more complicated. So when I worked and lived in England, we had lots of birds in the garden. So in that case, I wanted to know their name, so I bought a guide, a key. It's called a key to bird recognition. And it started like this. The first question was bird size. And then it was not like in centimeters, it was like at the bottom, it was a chaffinch or finch. Finch in Czech is vrabec. Then it was something like, what was the second one? I don't know. Here was the blackbird was somewhere here. Blackbird, then you have a crow, and then it goes to duck, I don't know, goose. And then at the top, we would have an eagle. I can assure you that nothing like that ever appeared in our garden. But so you can have, so that's interesting for a couple of things. So these are technically like just a set of possible outcomes, but they are ordered. So there's some ordering. You can have completely unordered things like there could be a second decision would be black, white, and other. Yeah, so you can see that immediately some advantages of a decision tree that you are not related to numerical values. And this guide, I noticed later on, showed that a decision tree could be also a DAG, a directed acyclic graph, because sometimes you can end up in one decision through different branches. Because, for instance, there is a bird which is somewhere between a blackbird and a crow, and you could have made a mistake here. And in the end, all the other things were pointing one way. So the decision would be reached through two paths. Of course, it can't be cyclic. What's the point? And okay, so now I guess everybody understands how decision trees work. That's actually one of their biggest advantages, clear interpretability and user acceptance. So if someone has some issues about how decision trees work, please tell me in the chat or say something. Otherwise, say all clear, and we'll go into the pros and cons. So over Christmas, I was watching some videos about how to give a lecture. And they say, well, if you ask a question, you should wait 7 seconds. It looks like eternity, but you should give people the chance to respond in 7 seconds. I thought I waited like 3, but you should say something in the chat. Decision trees are clear at inference time. Like this is called inference when we make decisions. So let's check. Okay, at least someone. Fine. So now look at the pros and cons. And maybe you can find something that's even not on the list, because it's so simple that you might come with some idea. So first of all, maybe I will start with point 2, sublinear in the number of classes. Yeah? So if we have a binary decision tree and we have k classes, the depth would be log 2 of k, and it's easy to see that, first of all, we really don't worry about the number of classes, so we can have any number. So k could be much bigger than 1, and with no problems whatsoever. And the decision is fast because we can ask log k questions to get to a leaf, which will lead us to a decision. So it's fast in decision time. It's sublinear in the number of classes. It's intuitive and interpretable. Often, this is not necessarily so, because, for instance, at this level, at every node, you can have, so maybe x2, 1, and this will be x2, 2, could be some complicated function. So it could be, for instance, that you have a SVM-based simple classifier here. But in principle, the most common way how decision trees are used, you pick one of the features and you ask which, like, if it's smaller than something, if it's greater than something, or some subset is satisfied. Look in the throat. Is it red? Yes, else go here. Yeah, very simple. So as a xi could be discrete, which means just from a set, which another continuous, categorical, ordinal. Ordinal means with ordering. Yeah. So, and that now 5 is very important in medical. So the property 5 says that you might have in principle a very large number of measurements. Imagine a person coming for a medical checkup. The number of things you can measure is enormous, starting from the temperature, I don't know, sweat on the skin that you see immediately, all the way to blood analysis and some very expensive scans. And these days you have so many scans that the amount of measurements that can be taken is enormous. Of course, we don't take them all. We take one at a time. And not only we take one at a time, but the measurements we take might be a function of prior decisions. So say the guy comes and you say, do you have I have a sore throat. Fine, look in the throat. If he says, I don't know, I'm coughing, maybe you do completely different measurements. So we have talked about some sequential decision making in one classifier. We touched this idea that you don't have to take all the measurements at the beginning. You don't have to assume all the measurements are available. We were talking about a system where we take measurements one at a time. Which classifier was that? So someone should know. I'll have to create another display on my screen to count for 7 seconds. So surprisingly, nobody remembers, but it was AdaBoost. Eh? If we think about AdaBoost, we said, well, okay, we evaluate the first weak classifier. And then we evaluate, formally the weak classifier is a function of x, but usually takes only some measurement. And here we could, for instance, already decide. And we were measuring x2 and calculating x2, well, h, the second weak classifier. And we were adding the result with alpha 2, alpha 1 to get a strong classifier after second stage, and so on. But no matter what happened, no matter what the result of H1 was, we always took the same H2. The weak classifiers were ordered, they were calculated, And in the end, we got a fine, strong classifier. In decision trees, this is not the case. So the second measurement could be different, could be the same, but we are taking only a small subset of the available measurements, which makes it possibly cheap, and we can make sequential decisions as well. So it could be that somewhere the tree finishes very early. So I don't know. Is the bird the size of a goose? Yes. Does it have an orange beak? Yes. I don't know. What else? Done. Whereas in some small, let's say blackbird size of birds, you can go very, very low down the list, and you need to ask many questions to get the right one because they are very common. Okay, we can do sequential decisions, which means we can stop early, and that could be fast. Then there is a degree of robustness to outliers, unlike in the linear classifiers.
I'm sorry, Professor, can I just step in?
Yes.
You said that we classify, in case of AdaBoost,
yes.
We classifier H2 doesn't depend on the we classifier H1. So
Yes.
it is always the same. But is that true? Seems because we select we classifier H1, then we adapt the weight of the badly classified results, and based on that we build or we select H2.
Yes, yes, yes. So maybe I was imprecise. Thank you for the question. That's a good question. So, of course, at learning time, the choice of H2 depends very, very heavily on H1. Somehow, because H2 is a classifier which works well on those examples which were weighted high after H1. What I'm talking here is at inference time, at decision. So once you train your classifier, and you have your strong classifier, which is this linear combination of the weak classifiers, for every object that you'll be classifying. So now we are in decision time. Learning has been completed. We have our strong classifier, which is we have our alphas and our weak classifier selected. And then we are going to, someone sends us an object X, some vector maybe, or a set of measurements, and he wants us to make a decision. And on that object, we will now execute always H1, H2, H3 up to Hn, every time the same, at decision time. Whereas in a decision tree classifier, the trajectory you will go through the tree depends on the object itself. So for different objects, you will make different measurements. For different objects, for AdaBoost, you will always evaluate the same weak classifiers. You might terminate early, but that's the only thing you can do. Is it clear now?
Okay, thanks. It's clear now.
Yeah, fine. So we have degree of robustness to outliers. So if someone tells me, well, the bird in your garden, I saw it, it was 3 meters high, big. Well, it doesn't matter whether he reported 3 or 5 meter wingspan. I will go into the eagle category here. And the fact that the measurement was an outlier, well, very, very noisy, might not make a difference because we are only thresholding. Yeah? Whereas if you have a linear classifier, something like SVM, so if we go to SVM here, and in SVM we do some dot product, if one measurement here is corrupted significantly, the dot product can go anywhere. Yeah? Whereas in the decision tree, you could even cover it. You can even get some robustness in this form of saying, well, if we were close to the boundary of a decision, we could end up in the same decision regardless of the trajectory. Different scales between features are not a problem. That comes from the fact that we are not doing any linear combinations. Deals with additional information. Now, this requires a little bit of extra explanation. So imagine you build a decision tree. So I'll draw another small decision tree, something like that. And this might be, let's say it's about diseases or maybe birds. Okay, let's make it birds. And here we'll have like some bird 1 decision, bird 2 decision, bird 3, and bird 4. And now it is possible and very easy when you do the training set to list all the birds that were observed, information about them. You can store it in the list of the tree. And maybe the observation could be something like time. Or it could be time when you observe the bird, or maybe duration of his visit, or maybe location in the garden, on a tree, on the ground. So if someone wants to know, okay, what if I recognize the bird and I want to know what time do they usually arrive in the garden, I can easily find other inference about the class. So I can get inference about, I can make other statements about the objects which fall into the certain leaf. So for instance, it could be that some other part of the tree, okay, or maybe think about it as a disease, and you can ask people, where do you come from? So it could turn out that at the beginning you are only interested in a decision tree to discover the disease, but after a while you can start asking, where do the people with this disease come from? And it turns out that there might be some special problem, I don't know, in water supply in some area. So you can store additional information. You can think about this as a tree, like not only a decision tree, but some sort of organization of information where it is easy to store additional information. That's exactly the 10. And you can use the same technique, like when you are using the training set, you know that your decision tree will not be perfect. So this is the decision, but actually you will have the number of class 1, number of class 2, class up to class K examples. And this is the, let's say, total in leaf L. And you can make the estimate of probability of class 1 given leaf L.
Excuse me, Professor, can you move the paper to the...
Yeah. So that's done it. So you can estimate the probability of each class in each leaf. So not only you have, of course, the decision is argmax number for K in the leaf L. So this the hash is the number of examples. So this is your decision. This is decision at the leaf. But not only you have the decision, you also have the probability. So if you have the probability of the correct decision, you also have an estimate of the error rate of your classifier. So that's all good. Okay, we can also use leaves for regression problems. So for trees. So for instance, you can be asking the price of dollar in 1 week, and then it could be something like, I don't know, has the stock exchange gone up last week? Yes or no? Here, is it summer or winter? Summer here, winter there. Now, this is now a situation, I don't know, is there a war happening in Africa? Yes or no? And then down here, you will be, you get a set of examples and you can write a function y f of x with some parameters alpha to find the regression function to regress a real variable. So you can use decision trees not only for categorical decisions where it's sort of natural, but you can also use it for regression. So far, if you think about it, all is excellent. Okay, the sublinearity. Okay, so there's a question. if we have K binary classification and then we have 10 features, we should ask, we can ask one question in principle, yes. Okay, so okay, let's say the question of sublinearity of K came up. So the interesting thing is what happens if K goes really higher up than 1. Yeah? So if you have two classes, we are really not interested in complexity of the classification as a function of K. But as the number of K goes up, for instance, in SVM, you have to do some trick called something Kessler construction that increases your space linearly with the number of classes, which is very difficult for very large K. Or you have to, like in AdaBoost, you have to do some new tricks. You have to generalize the training procedure. Here, as you will see in a minute, you just you do not have to worry about the number of classes at all, and your number of leaves will not be a function of K in a linear way. Now, when you talk here about the number of features, that's a different story. So we have so one can talk about the complexity of classification as a function of D, which is the dimensionality of the feature. And you can clearly see that, for instance, if you have a SVM, a linear classifier, it's linear. The decision time is linear in the number of features. Then, of course, then there's a dependence on the number of classes. And in most methods that we talked, with the exception of nearest neighbor, we covered the two-class problem because, okay, not true for networks. So for most, we talked for two classes because the generalization is difficult. For neural networks, it's quite fine. You have the part which does feature extraction, and at the final part, you have usually the softmax or some linear logistic regression. So if you add, if you start adding K, you have to be adding one more outer layer neuron. So this is also, this part is linear, but here it's even better than that. Yeah, exactly. Yeah. So what Jan writes it right. It means that as I increase K linearly, the complexity of the tree will not grow linearly. It's true, for instance, in networks, in deep networks, neural networks, if I increase K, some part will stay constant and some part will be linear. But here, nothing has to be linear. Yeah. Okay, now how many questions you have to deal and so on, that's related to training of trees. And now this is the one and only, but super important weakness of decision trees. There is no well-justified learning algorithm. So if you look at SVM, that would have been the, it would be probably the best justified learning algorithm. You say, okay, fine. So if we think about SVM as a good example of a well-defined training algorithm, someone said, okay, in SVM, someone gave us a vector of observations. That's the weakness. We had no choice. Sometimes it's a weakness, sometimes it's obvious. Like if you are doing face recognition, you have the camera image of it and it's fine. And then we said, okay, we are able to find, let's say, a classifier which minimizes the error on the training set. And also it has very good generalization. So together it gives us a very nice upper bound on the empirical risk. And this is really, really what we care about. So this is what I mean, a well-justified machine learning algorithm. You say, well, if you have a small error on the training set, and if you have good generalization, which SVM achieves by the margin, you will have a small error on the unseen test data, which is modeled by this error that you will have, the risk that you will have on the classifier, and that's the best you can hope for. Now, of course, we have this limits that this has to be numerical and things like that. You cannot do any sort of interpretation is very difficult. You you cannot do early decision making, you cannot do sequential decision making and some other things, but we have a well-justified machine learning algorithm. The weakness of decision trees is that they can overfit a lot, and there is no well-justified learning algorithm. Now, to show the overfitting, I'll give you an example which was published after the Obama-Clinton primary presidential election, and you could see that you can fit data with a decision tree quite easily. Yeah? So, but what it shows why decision trees are so popular. So, because the interpretability is very high. So, if we wanted to predict the win for Obama in a certain county, so the first question you can ask, is there more than 20% of the population black? If they were black, Obama wins. Notice they don't say he wins, but wins with 383 to 70. So again, if you made what we see are three things here: sequential decision making, early decision. This one question, you will get an answer which has like 70 out of 450, so something like 15% of error after one question, and this is good enough. Interpretability clear. If it's not the case, we have to go, so we ask another question. Is the high school graduation rate higher than 78%? So probably if it's not higher than that, this is a very sort of socially disadvantaged neighborhood with lots of problems, because in normal, I would say, so in the Czech Republic, there is not a single district where there would be less than 78% graduation from high school. So if this is uneducated, less educated voters, they go for Hillary. So now we are not black, reasonably educated. So the next question is 87, which means sort of highly educated. You are educated, you like Obama, that's it. Now we are sort of medium educated, not black. And where is it? So Northeast and South goes for Hillary, West or Midwest, still unclear, and so on, all the way down. So of course, this is a tree which we don't usually study like in machine learning. In machine learning, we create trees to make decisions on new data. This is pure interpretation of a tree. Yeah. So we have some data. It happened once. Nobody will. Hillary will never ever have another primary election contest with Barack Obama. So this is an example of using the tree for interpretation purposes only. But it means that, okay, if we learn how to train trees well, then we can use them only as a terms of interpretation of data rather than future decision making. Okay, so okay, so let's see an example how we could how a decision tree could work, and perhaps we'll use this example that you are familiar with. That's close to that one we had in AdaBoost, if you remember. It's like a Gaussian with a center at 0, 0, and then a noisy circle with radius, I think it's something like 1.5. So, and let's say we restrict ourselves to horizontal and vertical cuts, similar to that AdaBoost example. We can choose to threshold at some place which minimizes error. We'll formalize that later. The classification will be shown at the bottom left, blue on the left, red on the right. You can see that in the left subtree, you are making a very small error. It's like 2 out of 86. So we are somewhere at 2.5%. On the right, the error is very high. It's around, I don't know, 40%. Okay, then again, we cut to minimize the error. And at the right, we also have an almost perfect classification. 62 out of 63 examples are blue. Here we split. That was some sort of a quite small split, but it's already 2 errors out of 13. And this is the ambiguous class. And now we'll start cutting horizontally. And in the end, we end up with something like, here you see on the left, we have some, I would say, almost degenerate leaves with one example each. So that's the possibility to overfit. You see that this is this like red line is a clear overfit. The same thing on the right here. So in the middle, we have some, well, this has a 4 out of 31 error, but in the end, we got something which is a very small error. The decision boundary doesn't look at all attractive. We know this, the optimal, the Bayesian decision is a circle, I think with radius 1. We looked at it before. So not very pleasing. So another example, before we go into the methods for inferring trees, is an example which is completely discrete and showing that you can use decision trees for observations made by humans rather than measurements made by machines. And this will be an example about whether you should wait or not wait in, or whether your guests will wait or not wait in the restaurant. So what they call here attributes, which is yet another word for what we've been using, like measurement, observation, feature, attribute. And here there are sort of answers to questions. So prediction, whether you stay in a restaurant and wait for you to be seated, depends on whether there's an alternative nearby. This is obvious. If there's no alternative, you don't want to walk for 1 hour. The bar to wait in. So the bar here is like an area to wait. So if you have to wait on the street in the rain, probably you try to move on. Is it Fridays or Saturdays? Probably more difficult to find empty space. Are you hungry? If you are hungry, you might be more, well, we'll see what the people are inclined to do. Is this full or empty? I actually thought that if it's empty, it's a reason for staying. Actually, we will see that from the data, it will be the other way around, because maybe there's this guidebook rule that if you see an empty restaurant and nobody local is in there, probably it's too expensive or not good, don't go there. Price range, whether have you made a reservation? It sort of looks strange, but my experience from the US is that if you make a reservation, it still doesn't mean that you come and there will be a table allocated to you. And it's just like you go to a different queue rather than having a reserved table. Type of restaurant and so on. And okay, the last one is how long will you wait? So we have a training set of 10. In here we have all the attributes for all the data points. Or by the way, you could see that both the training procedure could easily use data which do not have all the attributes. So that's like missing value problem, which we touched with EM before. So let's say I make an arbitrary decision tree. So fine, a decision tree would take one of the questions, and if nobody is there, false. And now I have to decision to wait. So if there's nobody, I don't wait, I run. If it's sort of medium, that's which means there is like some empty space, but it's not full. Okay, then I stay. That's why I came. If it's completely full, then how long will I have to wait? If I have to wait a long time, I walk away. If it's short, I stay. If it's somewhere in between, it depends on whether I'm hungry and there are alternatives. So if I'm 10 minutes, it depends on my hunger. If I'm not hungry, I stay, blah, blah. So this would be one decision tree, which might be like, this is your advice, how you should behave in the Los Angeles area if you want to get good food and don't wait forever. Now, the classical methods of building, or it's called induction, or learning of a decision tree, is this top-down induction of decision tree. So I think they like this word induction. It's nice, it creates nice symmetric palindrome. And the main thing here is that the top-down means starting from just a pure node and being greedy. So of course, we are here like we are greedy in terms of building it, so we can forget about global optimality, but we even have a problem, even if the greedy strategy is greedy at the level of extending every branch of the tree, we still have another problem, how to define the best attribute. And effectively, it's a recursive procedure. So you are at a certain part of a tree, on the set of examples that fall into your part, select the best attribute and go recursive. Extremely simple. The pruning phase, the pruning phase, I wonder, maybe you don't know, the word pruning is what you do with fruit trees to keep them like not too branchy, so that they would, I don't know, obscure each other, the branches. So this is usually a set of hacks. So this is completely heuristic, this part. So we are in some sort of like quite unsatisfactory situation. Yeah? So here is a more formalization of the problem. So we have a parent node which will split into k, let's say, child nodes, and we need a splitting function which will map the set of points into the subsets. It's a partitioning. So in here, it's a partitioning, which means that every example will end up in one subtree only. By the way, I have played maybe 20 years back with decision trees where this need not be the case. You might have a situation where some example goes multiple sub-branches, but then you have to be very careful not to explode and in terms of computational efficiency, because you might be going into many sub-parts. But the classical decision tree has this property. Every example and then classified object will end up in one subtree. So this means in at most one, and the second condition means in exactly one. So it's a part that you partition the examples that fell into the parent node. And the splitting function has some parameters that define the splitting function. For instance, thresholds. You can have k equal to 2 or greater than 2. K equal to 2 is quite classical. For instance, the early versions of AdaBoost were often using this type of simple decision trees with K2, which are called decision stumps. Stump is what is left after a tree when it's cut down. So it's really like a tree with one, which splits into 2 branches, and that's it. Okay, so the most common method is that the function that you use to choose your split function is maximization of information gain. So this relates to entropy, which is on line 6. So, okay, entropy, when is entropy minimized? It would be minimized when Pj is equal to P. So if there's only one is equal to P for one class and 0 for all the others. So if all the examples in my node are from the same class, my entropy is 0, so is actually error in that node. And I am in a state which is satisfactory. So minimization, the reduction in entropy, seems to be a good goal. Like one can, and we'll come to that later, one can minimize the error rate. Yeah. So HP is the entropy of my current parent node. I look at the entropy of my child node. Each gets the weight according to the proportion of examples it gets, and information gain is defined as the difference between these two. So here I made an arbitrary choice of minimizing entropy, and this choice is sort of guaranteed, tested in practice that it works quite well, because the minimizer, you are somehow starting, if you start with a maximum entropy situation where you start in the parent node and maybe all your classes are represented equally, that's the maximum entropy. And through the decision tree process, okay, I have to switch here to the paper. So through the decision, you would like to have a distribution which goes something like one peak for some class here, and in the meantime, you want to get to something which is far away from the, say, uniform, close to uniform distribution. This depends on your prior probabilities, of course. Okay, so this is the example how the information gain would work on the example of the wait or don't wait at a restaurant example. So usually the procedure, that's another thing, is no way sophisticated. You try all the possibilities, you check their information gain and choose accordingly. So again, brute force greedy. So imagine that we try to choose whether to wait by the type. So in the examples given, in each of those restaurants, we have examples exactly 50-50 wait, not wait. So if we ask, should I wait? And the first question is, which type of restaurant have you just arrived to at? You get no information gain. That's not a good question. If you ask, however, about the number of patrons in that restaurant, if there are none, the decision is leave. So this is a 0 entropy node. If there are some, you always stay. This is also a 0 entropy. And if it's full, it's like 2 to 1. So it's not easy, like from the top of my head, to calculate the entropy of 1/3, 2/3 distribution. But here we have 2 zeros. So we had entropy of 1 bit. It was 50-50. Here we reduce nothing. And in the second example, we reduced from 1 minus, the first is 0, the second is 0, and then we have 1/2. And this, we reduced the entropy by half a bit. And this is what you get after making sure that each example ends up in a correctly classified node. So here you go to the depth that will give you 0 error, which might not be possible, but here it is possible. So you see, this sort of gives you a reasonable strategy. So that's the interpretability of the decision. How many patrons? Nothing. Go, some. Stay, full. Are you hungry? No. No. Go. Yes. Where are we? French, stay. Italian, go. Burger, stay. Thai. We have to ask a question. Is it on Friday, which is probably, I don't know, busy? So it is, yes, stay, because you would have to wait anywhere and else go. Fine. You can, so this is just maybe formal definition of what was happening. We have a training set on the input, like in all other supervised methods that we looked into. We have a class of allowed splitting parameters. So in this case of the bar weighting example, all our things were, we had binary questions, yes or no. So it was very easy. We had 10 possible attributes and there were no parameters on it. We start with P equal to the full training set. So that's the P would be the list of, say, training points at the example. We evaluate the argmin of this part of the information gain. If you remember that information gain is entropy minus this term, so we can minimize the this term I would call average entropy of the children. We take the one that minimizes it, we create a subset, recalculate, and then we do recursively on P1 to Pk what we did on 1. Trivial. And of course, if you looked at books on training decision trees, you'll have lots of hacks and ad hoc rules which improve things. But essentially, it's this simple, greedy, and there is nothing. Well, there's one thing which is significantly better, and we'll get to that soon. So you can do the same thing on just replacing the minimum average entropy by minimum average error. That would seem to be more directly related to what you want, because in the end, this is, let's say, this would be the error of a classifier that would stop at the current situation of the decision tree. So, and that's really what we want, this to be low. But it turns out that this is super greedy, that usually this does not work. It's often the case that you might you end up with trees which look like this, where you make a couple of perfect decisions. So you will maybe cut, so maybe you have 1,000 examples here, and you make a decision that splits into 995 and 5 examples which had 0 error. Often, this is what you get from this type of optimization. So although you are working on a decision function which looks close related to what you want in the end, this is the quantity that this is the, at least it's the error on the training set. It's what you want to minimize besides generalization. But there are why is this, like, if you think about it intuitively, why is this minimization of error worse than entropy? The problem with the error is that if you have quite, say, the error depends only on the class which is the most represented in the subtree. So if there's one class, you only care about this class, because the error, let's say if I have a class which is maximum, let's call it hash max. So the error is the number in the leaf minus the max divided by the number. Whereas the entropy, it's not only, so to reduce the error, you try to maximize the number of examples from the most common class in your subtree relative to the number. Whereas the entropy, it can do moves like, let's say we have a uniform distribution and you split it into 2 halves. One half of the tree has half of the classes and the other one the other half. So we have reduced the entropy very significantly, whereas the error is the same, because here, okay, you can pick one of the maximum, which is almost the same for everywhere. So you would say, okay, go to the left, try to find two classes where the error is the smallest, but it will be almost the same for all the classes. So you work on one class only, whereas with entropy, you work on the whole distribution. Okay, so if you don't have a good method, and this is quite common in computer science besides machine learning, go random. Maybe randomness can protect us. So what if we take, it's very easy to do such thing, build a tree where the splitting functions are random. If they are completely random, this is called totally randomized decision trees. So it would make every decision completely random. Now, you can have variants of this. For instance, how can you randomize the building of a decision tree? Random splitting function, or, for instance, random subset of training set points considered. You can see that these things work against overfitting. So there are like two or three, maybe two lines of justification of these randomized trees. And one is, okay, let's say we create a forest. As we all know, forest is a collection of trees. And let's say we have tree 1, and the tree is some mapping from the observation to this, to say the class. Okay. Then we have tree 2, and they are built randomly, and they will give us some decision 1, decision 2, decision 3. And maybe they will give us not only decision, they will give us a probability 1 of a given for all the classes. So it will be a distribution. I will put here like a vector. So, and then we can say, well, if we have all these decisions, we can do an average on that. If we, for instance, assume that this is noisy, and because these were built randomly, the errors on these decisions are random, and it will cancel out the additive noise. So the idea came, like, people were proving theoretically that if you are able to create independent estimates of the posterior probability, then we could remove any biases by averaging. So one can look at this way, that perhaps we have, I will do it in 2D, we have this space where our observations are, and then we do a random tree, and the first tree does some splits like that, and then it estimates the density here, the density there. Of course, if you then want to classify a point which is here, you are not optimal, because you are estimating density in this area, not in this one point. But then we have another decision tree, which might have cut this way. And then you would be estimating the probability of the class red using this. It will be some sort of simplex, intersection of half planes. And then you have a third decision tree. And the third decision tree might go somehow like this. So we get different estimates of the probability of the class at the red point, and through averaging, possibly averaging. Okay, there is a whole theory about this aggregation operator. So such trees are, there have been, let's say, there have been around 2010, these were the most used industrial strength classifiers. Because of all the possible things, you can imagine that this training using random decision trees is very easy. You get the probability by just estimating the densities in the leaves. Through averaging, you improve your estimates and you are fine. So these days, often, let's say, the most popular in many areas, but in many areas are the deep nets, but this can work on any type of data. And it has one huge advantage, which I haven't really talked about, which is quite problematic for instance, with deep nets. And it's something, and I will write it here as online. Imagine that you are using this to predict user preferences, and it's some examples become obsolete and some examples are new, and your decision tree, the decisions have to be shifting. Now, what does that mean in terms of decision trees? So all your examples, and that's coming back to this additional information stored, can be stored at the leaves. They are stored, they could be stored maybe as X, which is not important, all the observations around them, the class K, and maybe a timestamp. This is the extra information which is not important for a decision. But if you want to remove everything with a certain timestamp, well, it's very easy. So you can easily update your classifier as new and new data come in. Like, what does it mean in learning, say, deep nets with gradient, the stochastic gradient descent, if you want to remove some examples? Well, okay, so you remove it now. Well, how do you update the gradient? Not easy, yeah? Because somehow the information from that example is stored in all the weights of this deep network. Whereas here we have random trees. So these decisions might have not been, like the splitting functions were not function of the X. So this random cutting of the space into multiple pieces has this random, it's very close to hashing and nearest neighbor methods when we're talking about KD trees. It's very easy to update your classifier, remove examples, add new examples. Very easy. So in the end, like many of those classifiers that we talked about, decision trees had their heyday, let's say between 2005, 2010, because they are sort of interpretable, practical, can work on non-numerical data. You can update them. It's very fast. It's usually quite easy to debug, to check. Still, I think they are very useful. One can try to use this heuristic top-down approach. There are books about this, there are systems about that, about rules how to remove branches and things after this procedure and so on. I think that if people, if you do real machine learning, which means machine learning, not person playing with a tree, these random decision trees have many advantages. It's quite interesting to use. Of course, you use one of the important parts, or you lose, which is interpretability. If your decisions are randomly chosen, okay, totally randomly chosen, use interpretability. If you say, well, I will choose here we have a splitting function S, which we choose some random subset S prime and take the best from that subset, then the interpretability might be kept. Okay, preserved. Fine. So that's probably all I wanted to say about decision trees. Questions? Okay, so I think it's not a problem to finish early. This lecture is sort of, I would say, the easiest in some sense, because most people have intuitive understanding what decision trees are, and we do not have any sophisticated, complex optimization procedure or clever way of selecting the cost functions. And what has happened in the literature on decision trees until the random trees, where sort of like fixes that somehow, I don't know, split branches, add branches, cut branches, prune branches. And I think it's not worth going to the course. If someone starts doing that, I mean, if at work he needs to use decision trees, then you can take a book and write something like, give me seed 4.5, like that's a famous tree inference algorithm. Read all the tricks and read the books written about that. But because these are not well justified, and I think it's not necessary to explain the tricks at this elementary level. Okay, so we'll ask more question, Paul, and then
I would like to ask, will there be homework from the trees?
I think we have no time for that.
Oh, I also think that's why I'm asking. And